Mic. Okay. Put it on like this, should be on. If this can fit in your pocket, no problem. Yeah. And then you can either clip it or, yeah, exactly. Yeah. So, okay. Hello, everybody. So today we'll have just one talk, 40 minutes, and then questions following. And we have today Ehud Behar. He's a professor of physics visiting from Technion in Israel. His research revolves around experimental high-energy astrophysics and observing the most violent events in the universe, for example, accreting black holes, stellar explosions, and plasma under extreme conditions. His group developed the Gali detector, which introduced an innovative method for localizing gamma ray bursts. And he earned his degrees at the Hebrew University of Jerusalem and to conduct postdoctoral research at Columbia University before joining the Technion. He was also a senior MPP fellow at the NASA GSFC and a professor at the University of Maryland College Park. At the Technion, he holds the Dr. Philip and Sarah Gottlieb Memorial Chair, and he's the former Dean of Physics and former Director of the Asher Space Research Institute. He's also a member of the Science Working Group of the JAXA CRISM mission, and he's currently visiting the MIT for 1 year, right? Yeah, to work on CRISM observations. So it's going to be next door if you need some follow-ups. I think he only signaled today as an available date for meetings, but I mean, he's next door, so don't be shy to write an email, okay? So today's talk is gonna be about X-ray spectroscopic insights into the microphysics of collisionless shocks. And I'm gonna give you a warning when it's 5 minutes.
Sure.
Okay, that's it.
Thanks a lot for what was too long an introduction. We didn't need all of that. So yeah, as Giovanni was saying, I'm visiting MIT this year, and I call these series of talks as things I'm doing until CRISM gives us data, because I'd love to be here and tell you about CRISM, but we still don't have science data to talk about. And the topic that I want to cover today is collisional shocks, and what I think are interesting insights from high-resolution X-ray spectroscopy. This is the plan. I'll introduce collision shocks. I'll introduce what we call narrow radiative recombination continuum, RRCs. If you don't know what those are, I will tell you. I'll give some examples from stellar systems like colliding wind binaries, a planetary nebula, and supernova remnants. And the big question that I want to address and hopefully try to answer at the end of the talk is, what are the RRCs doing in these shock plasmas? Because as I will explain, they're not supposed to be there. We'll talk a little bit about adiabatic cooling and expansion of hot gas into the interstellar medium. And I have a really, really nice spectrum of ANOVA, YZ-RET, that I hope to have time. Well, I'll make sure to have time. Maybe give me a 15-minute warning, so that if I, I don't want to miss on that because it's really spectacular. Okay, so collisional shocks is something that I like to joke theorists invented to explain how, when we have bulk motion in explosions such as supernovae or stellar winds, that bulk kinetic energy is converted into heat and eventually light that we're able to observe. This goes back to the 1950s. The first paper I could find is the Hoffman and Teller, and I'm pretty sure that Zeldovich and his collaborators did the same in the USSR. It does appear in his book on shocks, obviously. And these shocks, they're prevalent. I mean, we see them in many places, both stellar, extragalactic. I won't talk about relativistic shocks today, mostly the lower velocity ones. And you can see this image down here from the Orion Nebula, where there seems to be a shock front coming from a stellar wind. So this has been for many years, as you see, a very convenient theoretical framework. But I think that a lot of the microphysics that are going on around the shock have not been explored, and for good reason. It's very hard to probe these small distances. I hope to give you some insights today from the X-ray spectra that I will show. Again, just examples: supernova remnants, planetary nebula, everything that's emitting a wind or explodes eventually is going to run into the ISM, create these shocks, and give us spectacular images, but also X-ray and longer wavelength emission. So just to explain what collisionless means, the idea is that the shock is not mediated through the Coulomb collisions. I'm going to show several slides with these calculations. You don't have to really worry about the details. I try to highlight the important parts in red. If you compute the mean free path of Coulomb collisions, here I took a 1 keV plasma. You find that it scales with the density, obviously. N, I'm going to use N a lot in this talk, the density. But for a 1 particle per centimeter cube typical ISM density, the mean free path is of the order of 10 to the 13 centimeters. This is big or small, depending on your perspective. It's small to resolve with a telescope. But when we say collisional shocks, we usually mean that the jump condition for the shock between the shocked and unshocked media is smaller than this, and therefore for sure is very hard to resolve or to get any insights on what's going on at the shock front. Important for this talk, of course I can't cover all the physics in collision shocks, but important for this talk is the temporal hierarchy. Things after the shock has passed, things kind of happen gradually on different time scales. What the shock does, it imparts velocity to the particles. So eventually, when they thermalize, the temperature that they get will depend on their mass and the shock velocity. So the ions, for example, because they're much heavier, are going to be much hotter than the electrons. Now, the time scales for obtaining a temperature, for getting a Maxwellian, a Maxwell-Boltzmann distribution, is also very different. Electrons get their temperature first, then the ions. Eventually, the two temperatures converge, mostly to the hydrogen or to the proton temperature, because that's where most of the energy is. Then ionization starts. Once the electrons are hot enough, they start ionizing. That's where, if you're trying to fit models to these spectra, the NEI models come in, where you're gradually ionizing the plasma from neutral to highly ionized, depending on the temperature of the electrons. And eventually, you're going to reach steady state, where you can use, again, for those who fit spectra, APEC or MECAL type models. I'm not telling you anything that Spitzer didn't realize in the 1950s, so I'm going to use his expressions to give you an idea of the times that it takes. I must say that this is a very simplified way of estimating the times. In real plasmas, there's a lot going on in terms of plasma waves, in terms of electric and magnetic fields that can change these times. But from what I read in the literature and understand in the literature, it's going to make a difference of maybe a factor of a few, not orders of magnitude. So let's put the numbers in Spitzer's expressions. You can see that the electrons will get their temperatures. I took here a 1 keV plasma, and let's just assume 1 particle per centimeter cube. Will take 10 years to get a Maxwellian distribution. The ions will take hundreds of years. The equilibration time between the temperatures is going to be, in this case, you see 23,000 years. And ionization, I was kind of lazy here. I just took the recombination rate, and in steady state, it's equal to the ionization rate. This is already the hundreds of thousands of years. So you see the hierarchy of what happens first and what happens later. And this is going to be important when we try to diagnose through spectra what's happening around these shocks. I like to give this as an example of why this happens. It goes back to very basic mechanics. Equal mass collisions are very efficient in transferring energy. That's Newton's cradle over there. You see the mass, the energy and momentum all go from one particle to the other. This is an example of an extreme mass where the floor here is the high mass body. And you can see the ball, which in this case would be the electron, the low mass, doesn't change its energy and momentum easily. Of course, this is an extreme where the ground is infinite in mass. Ions are not infinite, but it shows you how difficult it is to transfer mass, energy and momentum between low mass and high mass particles when the mass disparity is so large. And of course, the many body problem, which for our case is ionization, is more complicated, and then the cross section are even smaller. So there, I stole this, I think, from a review paper by Yaakov Vink. If you follow here the time on the, you see my mouse? Yeah, the time in terms of density times time after the shock, the electrons have the lowest temperature. They're they have the lowest masses, and over time they collide with the protons, which are depicted here as the white line. And the heavier ions have higher temperatures, but there's not a lot of them. So the protons dominate and everything converges to the plasma temperature. And if you can read the numbers, you see the scales are of order of 10 to 12 seconds, or hundreds of thousands of years. Yaakov has a really nice paper from 2003 where he claims that he sees the broad line, the dotted line is what a narrow line would look like, and it doesn't fit the data. A broader line indicating ion temperatures of hundreds of keV when the electrons are only keV temperatures. And once the electrons do heat to keV temperatures, ionization starts, and gradually over these time scales of, again, 10 to the 12 in these units, we get the steady state ionization of the plasma. Okay, so that's collision shocks and the time scales that I'm going to refer to in the remainder of the talk. What are the narrow RRCs? So radiative combination continuum. First of all, radiative combination is something that happens in plasmas all the time, but the key word here is narrow. These features are narrow when there's a mismatch between the ionization energy of the ion. The ions are ionized by hundreds or thousands of electron volts, but the electrons are orders of magnitude colder. And then what we see in the spectrum, this is the spectrum of NGC 1068. It's an active galaxy where we expect to see these. We see features like this. You see my mouse here? That look like an emission line, but it's not an emission line. It's asymmetric, where this is the ionization energy in terms of wavelength. And what we really see, this is a zoom into the RRC. What we see is the distribution of energies of the electrons recombining. You see here that it's not a line. It's asymmetric. And that's because the electrons are very cold, the Maxwellian is very narrow, and the feature looks discrete, as opposed to a very broad feature that you would see in hot plasmas. As far as I know, this is probably the best way to measure temperature in astrophysical gases, because you are literally mapping here the distribution. And since I told you that the electrons obtain their temperatures early, then in most plasmas, all plasmas that I know of, we're going to see a Maxwellian here. The temperature has already been established, even if it wasn't Maxwellian to begin with. And these widths correspond to several EV. Several EV in photoionized plasmas, which is this case in active galaxies, is natural because there's a hard X-ray source that ionizes the plasma to high degree, to high charge states, but radiation is not very efficient in heating. So the temperatures remain EV-ish, whereas the ionization energies are KEV-ish, and we see these narrow features. Now, I don't want to talk about photoionized plasmas. I want to talk about shocked plasmas, and I want to show you that we see RRCs also in shocked plasmas where it's not natural to find them because the plasma is hot, is very hot. So here's just a few examples. This is a colliding wind binary with a radiative combination continuum of carbon. And the authors here show 3 temperatures in the fit. I think it's 2 EV, 4 EV, and 6 EV. And you can see that very precisely we can measure 4 EV temperature in shock plasma that's much, much hotter. This example on the right is a planetary nebulae. The model is an APIC model, so you see it's a hot plasma. And you have to look very closely, and I'll show you, I'll zoom into this in a minute. You have to look very closely to find these narrow RRCs, but the plasma for the most part is hot. Here's an example from a supernova remnant down on the bottom left-hand side. Here, the temperature disparity is not so big. The gas or the X-ray source is, I think, 4 or 5 keV in this case, and the recombination continuum is 1 keV, so maybe a factor of a few lower. This is the nova that I want to show you at the end, so I don't want to spend too much time right now, but you can see in RRC where this is the energy or wavelength, and the very clean E minus E over KT temperature measurement of 2 keV, and all what's happening on the right-hand side of this black line I'm going to describe in more detail later. But my point here is that if we look carefully enough, we find RRCs in shock plasmas that are much hotter than the temperature, electron temperature that we're measuring in these features. So let's just look into, just to give you this one example of a planetary nebulae. Planetary nebula, if you're not familiar with the high energy aspects of it, there's a white dwarf wind that collides into the ISM. This is an image of BD plus 30. A reverse shock into the stellar wind heats it to X-ray temperatures, about 1,000,000 degrees in this case. And you can see that the 1,000,000 degree plasma model in the red model here fits pretty well. So we're confident that most of that it's called the hot bubble is emitting at about 1,000,000 degrees from the center of the planetary nebula. However, in spectroscopy, always they say the devil is in the details. I tell my students, your thesis is in the details. The thesis here of my student was around this tiny feature that is the RRC from several years ago. And if you zoom into this region, first of all, you see the model doesn't pick it up. And because the hot plasma model doesn't have those features, this is a Lyman series of carbon. This is Lyman alpha, Lyman beta, Lyman gamma. Back then, APEC didn't have the high-end lines, so we added them. And if you look really carefully, squint your eyes, there's a residual here that is the RRC that eventually in this bottom panel we fitted with the RRC. And you have to trust me that when you fit the width, you get a very precise measure of the temperature, about 2 to 3 electron volts, when, again, the plasma is much hotter. It's 100 or hundreds of electron volts. And that is the puzzle of this talk. I want to try to understand why or where or how we get these cold electrons to recombine in shock plasmas with the majority of the plasma that is much hotter. If there are any questions, by the way, just go ahead, shoot. Okay, this slide just comes to show the importance of high resolution spectroscopy. The same planetary nebula that I showed you before, measured with Suzaku. Suzaku had CCD spectrometers. And these authors identified this feature here that is the RRC as a nitrogen emission line. Nitrogen comes, again, for the specialists at 24.7, the RRC at 25.3, and you can't tell the difference with the CCD spectrum. In fact, at high resolution, you see this plasma is void of, there's no nitrogen here at all. There's no nitrogen, and you would confuse this RRC with the nitrogen Lyman alpha line if you didn't have the high resolution that, in this case, I didn't mention, but this is LETG spectrometer on chart. I want to say a word about the supernova remnants. So there are a few now remnants where these RRCs have been claimed. This is the best one that I found in the literature. You can see it's at very high energy, 8.8 keV. So that's the recombination of helium-like iron, very highly ionized iron. It seems to be conspicuous in the spectrum of New Star, up to that can record energies up to you see almost 20 keV here. But it would be really nice to see it in high resolution. And what I have in the bottom panel here is it's a simulation. As I told you, we don't have these data yet with CRISM. CRISM is for those who are not familiar, is a Japanese mission with a NASA calorimeter, a non-dispersive spectrometer that will be able to give us good spectra of extended sources. W49b is a pretty big source. Doesn't work well with X-ray gratings that don't have slits. And this simulation shows us that we might be able to measure this RRC. You see a very sharp feature here. And again, this wing, the high energy wing, will map the electron energy distribution. Here, a Maxwellian was assumed based on the fit of the New Star spectrum. Above it, you see the CCD spectra. There's a hint here of the RRC, but you really can't confirm it without the high resolution spectrum. Hopefully W49b will be observed in the next couple of months. I'll be able to tell you that we actually identified the RFC. Okay, so how can you get a combination of cold electrons with hot ions? And I'm running through several examples. Some of them you'll find in the literature. And basically, I want to shoot all of them down. The first one is that maybe like in active galaxies or in X-ray binaries, there is a photoionizing source, only we can't see it. It's hidden. In most of these cases, it's easy to rule out. Supernova remnants, there's no continuum X-ray source in the center. The Panera Nebula doesn't have X-rays. The central source is much too cold for that. The novae might have. There are papers in the literature that I think make a lot of sense, saying that the accreting white dwarf in the nova sometimes can be obscured. And when the super soft source emerges, if we don't see it, doesn't mean it's not there. It could photoionize the gas that we're seeing, but in most cases, that doesn't work. The second bullet here is that goes back to what I told you before. Early on, indeed, the ion temperature is much higher than the electron temperature. There is this disparity, but then you don't have ionization. You need the electrons to heat up to get the high charge states. So that can't be the explanation either. Plasma instabilities that result in radiative cooling, again, doesn't really hold water because recombination is a big part of the radiative cooling. So you can't cool without recombining. You need to cool the plasma to EV temperatures and still have the high charge states. That's probably not going to happen. Adiabatic cooling is harder to refute or to confront. This is the dependence of density and temperature in adiabatic expansion. So the idea is that you shock the gas, it heats up, but then it expands and cools. And if it expands fast enough, then the charge states will remain high, the electrons will cool. You might get this kind of recombination. Because of adiabatic relations, you would need, for example, if you want the temperature to go down by 2 orders of magnitude, you need the volume to go up by 3 orders of magnitude. That's pretty extreme. And in any case, the recombination rate depends on the density. So most of the recombination is going to occur early on when the gas is still dense, and much less when it expands. But there could be some cases, and I'll show in the next couple of slides, where maybe adiabatic cooling could work. What I'm trying to suggest here is that none of this is happening. What is actually happening is that the hot gas has a direct interface with cold matter. And this can happen in several places in shocked plasmas, and I want to demonstrate that here. This is a profile, the naive profile. We did this for the planetary nebula of radius, so this is spherically symmetric, and you see density and temperature. So what happens? The wind impacts the interstellar medium. This happens at what's called the contact discontinuity. So ejecta on this side, ISM on this side, and then a forward shock goes into the interstellar medium, a reverse shock goes into the ejecta, and what you get, this is the hot bubble. You get very hot, okay, this is 1,000,000 degrees. This is a hot gas that has been shocked from the ejecta. In this case, the forward shock isn't as efficient in heating the plasma. You see the temperatures up here. You see the densities in the top panel. See the density here jump at the shock front, and there's also a density jump here at the reverse shock front. And in principle, these 3 interfaces, this one in this case not so much, have hot gas on one side and cold gas on the other side. Same here, hot gas on one side, cold gas on the other side. Now, I told you that this is a theoretical picture of a collisional shock that is, mathematically abrupt. But in effect, it's, plausible, maybe even possible, or even can't be otherwise, that particles do cross the shock front. We know that the accepted mechanism for cosmic ray acceleration is actually particles crossing the shock front. So what I'm suggesting is that hot particles, hot ions from here, go either to this side where they're cold electrons, or to this side where they're cold electrons, and recombine very close to the jump condition region or boundary of the shocks. How deep Can the particles cross this? So you have to assume something about the magnetic fields. Collision shocks have to be mediated somehow by electric and magnetic fields. If you take a conservative magnetic field of the ISM, like a micro Gauss, you can get an idea of how deep into the other side the ions are going to cross. You see 10 to the 9. So this, again, is much, remember we talked about 10 to the 13 as the typical mean free path of Coulomb collisions. If they're magnetic fields, even weak magnetic fields, this is much narrower, and obviously no way to resolve it with imaging. The cold electrons penetrate even less. The Larmor radius of the electrons is much less. They're colder and lighter. Now, the time that the particle would spend on the other side isn't big unless the density is high. So you need the cold region to be densities of at least 10 to the 4 for recombination to occur, or just the particles will go back and forth. And in this case of a planetary nebula, actually, we know that the density on the shocked ISM side is about 10 to the 4, which makes sense for this kind of scenario. So the particles cross into the other side. They have to collide, either cool down or stay long enough to recombine in order to get this cold recombination effect. So these were the examples, and I try to give you an idea of what the RSCs might be doing there. I want to spend some time about cooling, because if you survey the literature, most authors will tell you that the RSCs are due to adiabatic cooling. That happens a lot of times with observers where the temperatures in their model don't match the measurement. Adiabatic cooling is kind of that joker that you can play and say, oh, well, it cooled because it expanded. That's why my model doesn't fit. But of course, adiabatic cooling is a real process. It needs to be considered. For Poorman's theory, what you can do is you can estimate times. 6 minutes for the 15. Perfect. Thanks. Yeah. Geometry comes into place when you talk about adiabatic expansion, and we don't know exactly the size of plasma, what was it, and how much it expanded, but you can parameterize it with the size that it started with. And I took here the typical, stellar wind or planetary nebula, or maybe even parcel of gas in a supernova remnant. And you want to compare that with a recombination time. In order for this scenario to work, the gas has to expand and not recombine. The recombination times have to be much longer. You see that for these parameters, they're pretty similar. Here you have the size, here you have the density again, because everything scales with the density. Now, for most of these cases, the adiabatic times are much larger than the very fast recombination. So there's no way that adiabatic expansion can beat the fast recombination. In colliding winds, planetary nebulae, and novae, supernova remnants are different. First and foremost, because their density really is low. These are very low density shocks, so recombination is slow, and maybe adiabatic expansion can surpass or be faster than the expansion. And the other thing is that also the temperature disparity, at least with the low resolution spectra that we have, it's not that big. We only require that it cools by a factor of a few, maybe an order of magnitude. So maybe for, again, given these judicial parameters, maybe adiabatic expansion can be faster than the recombination rates, and you could actually get RRCs that are due to adiabatic expansion. But in all of the other stellar cases that I've looked at, adiabatic expansion is way too slow to compete with recombination. So I wanted to look at this a little bit more in detail. And I gave undergraduate students the project of, why don't you compute the simplest case? There's a hot blob of gas, and just let it expand adiabatically into vacuum. Turned out, it took 3 students for me to realize this is a much harder problem than I thought. You'd think it's really simple. And one good student who said, wait a minute, somebody probably solved this earlier, found these papers in the 1960s and said, let's try to look at these solutions. So apparently people were interested in this, fluid dynamics problem. Hot gas, spherical, symmetric, one-dimensional, expands. What's the density and temperature profile as a function of time? And cut a long story short, the student Bari took these solutions. He computed them numerically. What you're seeing here, it's always x and T in these dimensional units. It's not too important here what it is. You start from a dense and hot, this is density. You start from a dense and hot region and it expands adiabatically. Very quickly, the gas goes down in density. Let's skip velocity, not so interesting, and temperature. So you see it cools, but with time, this is the time axis, it takes the gas inside time to cool because the central part of the blob remains hot. It cannot expand fast. So what we cared about are the recombination times, and what you see here, this is temperature as a function of time for different regions in the blob. You see the inner parts take a long time to start cooling. Again, because the inner part of the blob cannot expand right away. Eventually reaching an adiabatic curve, the dashed line here. The important plot is this one. These are recombination rates for different ion energy and temperatures, and this is the dropping temperature as with time, as the thing expands. And for the realistic curves, which is the red and purple here, you can see that by the time the temperature dropped by a factor, an order of magnitude, most of the recombination already occurred. There's very little gas that remains ionized after the expansion. So we might be seeing this residual if adiabatic cooling is the explanation, or at longer times, we're not going to see any recombination. The gas is totally recombined. If anyone here does hydrodynamic simulations, I'd be very happy to talk about how to do this, maybe on a numerical code, and see if this solution is really confirmed by numerics. Okay, so this is my 15 minutes on the YZ-RET nova. In terms of X-ray spectra, it's really, I'll show you, it's an amazing spectrum. It was very bright, 3.7 magnitude. It was a naked eye nova in 2020. It took about 70, this is the Swift light curve. It took about 60 or 70 days for it to brighten up in the X-rays, and then it also softened. This is the hardness ratio. So this was early on, it was clear that this is a spectacular nova. And on these days with the dashed lines here, XMM was triggered here. You see it pretty close to the peak. And Chandra LETG was triggered, I think, 40 days later. Now, the idea, again, for those of you who haven't looked at nova or don't know anything about nova, the idea is that the thermonuclear runaway on the white dwarf surface creates this explosion or outburst. And as the white dwarf or this source contracts, it becomes hot and the super soft source emerges. So you expect at some point the white dwarf atmosphere to emit soft X-rays. And when you look at this only at these data, that's what you think is happening. It's brightening up and it's becoming really soft. But we triggered, or I shouldn't say we, the authors of these papers triggered XMM and Chandra and got the following spectra, which don't look anything like a super soft source. They look like an emission line spectrum. The person who's been challenging me with spectra of nova for many years is Marina Oreo. I have to say, as a spectroscopist, these are the most challenging spectra to analyze. There are a lot of things in the spectrum that we don't understand. Sharon's my student who's actually writing the paper on this right now. What you see right away is that in RGS spectrum on day 77, the brightest thing in the spectrum is this RRC. I've never seen anything like this. I showed you before, you had to really look at the details to find the RRCs. Here, they're emission lines that we identify. I'll zoom into some of them soon. But the strongest feature in the spectrum is an RRC. So there's massive recombination with cold electrons going on. 40 days later, you can't see this here, but LETG observed the source, the spectrum. I'm going to show you some details soon, but also has these RRCs. It's much fainter. You saw the Swift light curves. I mean, the source is fainter. But what I want you to see here is, again, an APIC model in red. So for the most part, the plasma does look hot and highly ionized. You see lines of carbon ionized 5 times, 4 times. Here in the softer part, you see silicon and argon lines that are ionized many times. This is hot plasma. And nevertheless, it's recombining with cold electrons. So let me show you some of the details. And again, some of this is going to be for the spectroscopist savvy ones. And feel free to snooze through it if there's too much details. What you can tell, it's really nice to have two observations of the same event 50 days apart. Let me tell you what you can find right away. Okay, it's 40 times fainter. I told you that. The lines are blue shifted. We're observing this nova outflowing. And the outflow velocity did change, at least as far as we can measure in the lines. It's 1,500 kilometers per second, 77 days after the outburst, and 115 days after the outburst. This right away gives you a scale. It tells you that if it expanded at that velocity for so long, you already have to be pretty far, at about 10 to the 15 centimeters, if this is an outgoing wind, at least from the center. And this is only starting 80 days after the burst. I mean, for sure, it passed more than that. This very quickly rules out a photoionization scenario, because for photoionization balance, and I'm telling you, we're seeing the same plasma, the same charge states. If you go further away, the radiation goes down. The flux that the gas is seeing is going down, even if the source didn't go down. The other thing is that the temperature that we fit, it's not very hot, 70 EV, again, is the same on day 77 and on day 115. There's some broadening, some turbulent broadening in the spectrum. The lines are resolved. Again, same thing. Day 77, day 115, same broadening. And we're seeing RRCs in both epochs. Much weaker in LATG, but we see them. If you want to take one thing away from this diagnostic, and I'm going to prove this in a minute, is that this wind is very dense. Number densities of 10 to the 11 centimeter per centimeter cube. So this is the main feature, the RRC. This is the Maxwellian, about 2 EV. And there's this really interesting series of lines. This is the helium series. So this is n equals, again, in terms of principal quantum number. 4 to 1, 5 to 1, 6 to 1. Not only that's not diminishing, it's increasing. It's broad. It's very bright, much brighter than you would expect with the plasma model, with the APIC, for example. What we did is we tried to constrain the highest line that we can actually think is there in that blended region of high-end lines. My student did this figure of C-stat, some statistical measure, and found that going beyond about n equals 35, plus minus 10 maybe, the fit isn't accepting those lines. What can you do with a maximum level? You can do two really nice things, and both of them give you a density measure. One is something that's called continuum lowering. Again, you don't need to be an atomic physicist. Just think of the Bohr atom. You have higher and higher levels, and they converge to the ionization level. At some point, collisional ionization, you're going to ionize these by collisions more easily than or faster than they will decay. At some point, the collisional rate's going to exceed the Einstein coefficient. And when that happens, that depends on density. When that happens, that's the maximum n that you're actually going to observe. So if n equals 35, gives us about 10 to the 11 particle per centimeter cubed. There's another interesting feature in dense plasmas, going back to Teller. Teller did some really amazing stuff before the war and after the war. You know what he did during the war. Talking about Stark broadening. Stark broadening is the effect of splitting of lines due to electric fields, and in dense plasmas, ionized plasma, the electric fields are the neighboring ions. So as you increase the density, the ions come closer together, the electric fields they feel from each other are stronger, and the lines get broader. And at some point, you're not going to be able to tell the continuum in this Rydberg series from the last line. And Inglis and Teller have a very convenient formula. If you know n max, it gives you a density. And this also gives 10 to the 11, pretty amazingly. If you're familiar or you feel more comfortable with a more traditional density diagnostics, what's called the helium-like triplets, forbidden over intercombination. This is plotted here. You could have seen here, let me show that very quickly. In the spectrum, this is the forbidden intercombination. Usually there's a factor of 4. Here they're about equal intensity. That right away tells you the density is high. And again, you get the same consistent 10 to the 11 from the measurement. So this is dense plasma by stellar wind standards. And another thing that we're seeing, I might want to skip this, but just in a few words, is dielectronic recombination. again, for the spectroscopic experts, that combination is when you capture, an ion captures an electron and ends up in a doubly excited state. That doubly excited state decays, and we see the line. They're called satellite lines because they come next to the parent line. And we identified very broad and very strong dielectronic combination lines that are anomalous. We found this in a paper from a laboratory measurement. Same spectrum exactly. See Lyman alpha, this line, helium gamma, helium beta. And in the middle, these DR lines, this is a really nice second order spectrum where you can resolve them. We're actually seeing this line very bright, and these are very weak. And I'm going to skip the explanation. If you want to ask me about it later, it's a really neat explanation, but I'm running out of time, and this is really detailed spectroscopy. We could get a density from it, same density, 10 to the 11. I want to go back to the time scales because the first implication of a high density is, as you remember from the beginning of the talk, everything happens fast, much faster than before. If you compute the cooling times, yeah, you take a standard cooling function of a solar abundance, astrophysical plasma, and you put in the temperature of the nova, the density that we're measuring, this gas should have cooled within seconds. Yet we're observing it over 40 days. So that tells you right away that you need to constantly heat the gas. And that's probably what the shock is doing. The other thing is, because the cooling is so fast, it means that when you're observing, you're only seeing the gas that was shocked recently. You can't see gas that was shocked 40 days ago. That already cooled a long time ago. That means that again, in the spherical picture, that means that region of X-ray emission has to be really narrow. And if you take that cooling time times the velocity of that, you get about 10 to the 9 centimeters, which I hope reminds you of that Larmor radius where the gas is mixing. The other thing that's peculiar here is that if this is the shock velocity, I don't know, it's the measured velocity, then you expect much hotter temperatures of 4 keV while we're measuring about 100 eV. And I think the idea here is that the times are just too short. I computed the times that we showed before. Again, electron temperatures are going to get there, even at 10 to the 11, going to get there Maxwellian very quickly. This is all in seconds. Ions the same. Calibration times is getting close to a second, and then ionization time is going to be a few seconds. But the thing cools within 10 seconds. So I'm not sure there's enough time to reach the high temperatures and the high ionization states. The other thing you can do, again, to get an idea of the geometry when you have a density is compute the emission measure, basically the flux of these sources, and you get a volume. You get the volume of the source. And if you assume some geometry like a thin shell, again, you get something that's very narrow. This is a very low velocity. I told you this expanded already to about 10 to the 15 centimeters. It can't be very close to the center. That means that the shell is very narrow. And then all this from the RGS, 40 days later, probably the density went down by a bit. The volume increased by a little bit, but not by a lot. We expect it to decrease by 10 to a factor of 10 to 100 in density. Another neat thing, and this is the last detail, after that I'm going to wrap up, that we're seeing are these high-end lines that I pointed out before. This is, in my mind, really the smoking gun of a process that's called charge exchange. Charge exchange is when these highly ionized species collide with a neutral hydrogen and take its electron. So they recombine because this is an atom-atom collision. There's a lot of angular momentum, and they end up in high angular momentum states. This is the only explanation that I know that can explain such bright high-end lines. They're still too bright for most charge exchange models. Just to give you an idea, what we see is these lines from n equals 4 to 7, pretty much the same intensity. You can see it by eye here. And if you go to a nice review by Lee et al. About charge exchange, you see that you get a broad distribution in principal quantum number if the collision is at high velocity. We're somewhere between 2400 and 900, somewhere in the center. So I think the flat distribution in n probably means that we're seeing charge exchange of fast atoms running into our charged particles, or vice versa. That's the relative velocity. There's still a problem with the high ends that we're seeing. There's a very clear prediction of where you should expect the maximum population, and it pretty much goes with the charge. So if this is carbon plus 4, plus 5, we expect the maximum to see at 4, 5, whereas we see higher end lines. Again, I think that's an indication of high density and population in excited levels. But if you want to ask me about that. Okay, so this is the slide before last. What I think is going on in this nova is the following. Within the 100 days, the shock has moved about 10 to 15 centimeters out. That's pretty far. And interestingly, this picture matches a set of theoretical models by Achishus and Kato. This is the last paper, but they've been doing this for a long while, that predict a very thin shock, a very thin plasma source, which is not as far in their models, 10 to the 14. It's also not as dense as what we measure, but that's fine. Still, the overall picture qualitatively is the same. What isn't the same is that the nova here, or the super soft source, at least we haven't seen it. You don't see it. It could be, I mean, we could be viewing this from a different angle where it is obstructed from our line of sight. But what I think is happening, going back to our cold plasma features, is that we're seeing RRCs and charge exchange, evidence for direct mixing of hot gas with very cold gas. And that has to happen either at the contact discontinuity or at the shock front itself. The scales that we're measuring or implying, from our measurements are very small, nothing you can ever resolve, but they are kind of consistent from our emission measure, from our density, from computing how far particles can cross the magnetic fields of the shock, and so on and so forth. Just a few points to summarize. I think spectroscopy is a powerful tool to diagnose regions and physics that you can't do with imaging or with timing. This source doesn't vary very rapidly. The shock is slowly evolving. I think what we found here is that the collision shock jump is not mathematically abrupt. I mean, there's a region there where interesting physics is going on and particles are going back and forth. And in my mind, the nova YZ-RET is the best example of a very strong RRC. And you can challenge me if you think otherwise, but I've never seen any real evidence for charge exchange in astrophysical spectra, except for the solar wind and the solar system in highly ionized systems that are beyond the solar system, like this nova. Thank you very much.
Okay, we have time for a couple of questions.
As you mentioned, the possible origins of RRCs being like adiabatic expansion, but you ruled that out somewhat due to density and timing arguments. What about thermal conduction? If you have dense material that some of it survives the passage of the forward shock and is thus embedded in the hot ejecta and cooling it?
Right. So most estimates of thermal conduction are not fast enough. One. Two, thermal conduction would give you a continuous distribution of temperatures. And I didn't point this out, but I should. Thank you for that question. The fact that you see a narrow RRC means that there is very cold gas, the hot gas you see from the high charge states, and there's no in between. Because if there was a distribution of temperatures, it would have smeared out your recombination signal. And we actually computed and put very strict limits on, let's say the plasma is 100 eV, the electrons are 1 eV in our RRC, how much 10 eV gas there can be somewhere in the middle. And it's minuscule. There's none of that. The thing that also works against thermal conduction, by the way, in shocks, is probably the magnetic fields. It's harder to conduct heat when with charged particles when the magnetic fields are threading through your plasma. You're stuck on the magnetic field. So it's hard to go from hot places to cold places. But leave that aside. Just empirically, thermal conduction could be in place. It cannot explain the RCs.
Okay, any other question?
Hi, John.
As far as the simple adiabatic expansion cooling, my recollection is that for the supernova remnants, you really require that the shock go through a circumstellar medium. If you shock some dense gas around the supernova rather than just be like I said, or something like that, simply in order to have enough emission measure to see anything.
And you would put that at what, 100 particles per centimeter cube, or
Much more than that.
Much more than that.
What's seen in the supernova spectrum and so on could be quite a bit more.
for the X-ray source? So that only strengthens my case that adiabatic cooling is not going to work, because when the density is higher, the combination is going to be fast, and adiabatic cooling is not going to be fast enough to cool before we combine it.
It depends on where you put the supercell.
Right, right. Usually people think of adiabatic cooling in shocks as going like, with a bow shock, right? I mean, you can escape the hot region along the shock front. At some point you spread out. I don't know how efficient that, I think the spherical force, which is far from the reality, the spherical expansion is probably the most efficient adiabatic cooling scenario you can think of. But I'll be happy to talk about that more. I'm very skeptic of adiabatic cooling as explained by RCs in again, because there's no intermediate temperatures. They're only very cold. But your comment only strengthens that argument. Thanks.
Okay,
in the flux of the RC that would be useful in this case?
Yeah, so when I said emission measure, you can get the emission measure from the lines or from the plasma model. You can also get the emission measure from the RRC, and we get the same volume. Which again, that's also a very good point that I didn't stress enough. What I think is happening is because this shock front, or because this X-ray source is really so narrow and is smaller or maybe equal to that distance, the Larmor crossing distance, I think what happens is that the cold gas floods the entire shock region. So, and that's the way to explain. So the volume is the same. The volume that is emitting the hot gas and the volume that is recombining, I think they're very similar. And that comes from the very bright RRC. The emission measure of the RRC in the NOVA case is very high. Therefore, the volume that it occupies has to be large. Of course, we don't know that they really overlap in space, but it is consistent with that kind of picture. And the stellar winds and the planetary nebulae and in the supernova remnants, the emission measure is much lower. I mean, the flux of the RC is much lower, and this has to be coming from a smaller region, not the entire X-ray source that we're seeing. So that's a good point. Yeah, the flux of the RC tells us if you have a density measurement, which usually in remnants we don't. It's indirect evidence of the density. But here, when we have, I think, a very robust density measurement, that gives you the volume, gives you the size of the source, which is neat.
okay, any final question? Maybe I have a curiosity. So this, as you showed, seems pretty like a mechanism that could explain like what we usually
Sure.
see. So is there any other case in maybe observed but not recognized as such that could help building the statistic?
So I tried to survey the literature, and sometimes people don't even notice these features. They're so subtle. And I think they're pretty generic to, again, colliding wind binaries. Unfortunately, planetary nebula are faint. We don't have many grading spectra of planetary nebula. Supernova remnants, many of them don't. But again, we don't have good grading spectra. Supernova remnants, maybe CRISM will show it so that it's more common. So that's an excellent question. So far, the number of the sources where these have at least been published is not that big. Is not that big. But I think what really speaks volume for why this is interesting in terms of the physics is that these are totally different sources. Supernova remnants, colliding wind binaries, novae, planet. The thing that's common to all of them that there's probably a collisionless shock producing the X-ray source.
Okay, so let's thanks Ehud again.
Thank you.
Remember, if you want to meet with him today or just write me.